4.3, limits at infinity. First of all, I want to start with a few definitions, and we're going to start off with a function. So we have a function f, and let's say that this is what it looks like. That's our function f, going to the right and going to the left. And we want to describe what the function does as it goes to the right. Let's say, as it goes to the right, we describe it as the limit of x values going to infinity. And we want to find out, is it approaching any numbers? If it is approaching a number, it would be what we call a horizontal asymptote. And let's call that horizontal asymptote L1. Okay, so according to what we see here, the nature of this graph, as x goes to infinity, taking this graph this way, we see that it gets closer and closer to L1. So the limit as x approaches infinity of the function f is L1. Let's take another scenario. Let's take a second function, g of x, and let's say g of x does this. Okay, let's say to the right it takes off, but let's look at g of x as it travels to the left side. Let's see, the g of x travels to the left side, it gets closer and closer to a horizontal asymptote, and let's say that's L2. So to describe g, we would say g as the limit x approaches negative infinity. We have a value of L2, or horizontal asymptote, that's getting closer and closer to. So limits describe a value that is unique, that is getting closer and closer to above any other values. So these actually have solutions that are considered limits. Now, what are other scenarios we can have? Well, let's say we had the function f again, and we took the limit, and let's say we went to the right, and graphically this happened. Now, if that happens, what we say is that the limit as x approaches infinity of f of x is positive infinity. Okay, it's steadily going up. And it can also happen that f could go down, and that'll be a negative infinity. So there's two possibilities, plus or minus infinity. And the same thing could happen going back. Going backwards, we could have a function, let's say g, as x approaches negative infinity, could go up to positive infinity. Or g could go possibly to a negative infinity. Okay. So we would say that this limit exists here. These limits, these horizontal asymptotes, they exist. For here, we say that as a result that they're going to infinity and positive or negative infinity. Here they're unbounded. The limits are unbounded. Okay, now we're going to look at some specific functions, just saying general f and general g. Let's look at the function 1 over x. The function 1 over x looks like this. It has a horizontal asymptote of x equals 0, vertical asymptote of x equals 0, and a horizontal asymptote of y equals 0. The graph exists in the first and the third quadrants, getting closer and closer to the asymptotes. So as I take a limit of this particular function as x goes to positive infinity, we find that this particular function here, the limit is 0 to the right, and the limit as x goes to negative infinity from the left of the same function back here is also 0. This implies that if we have any function of 1 over x where the power here, let's say r, is 1 or greater, as you take the limit as x goes to either the left or right side, okay, to the right or to the left, we will get 0. And this is as long as the r, which is the power here, is going to be greater than or equal to 1. So any value greater than or equal to 1 will give you the same limit. Now let's talk about some of the properties of combining limits. Property number 1, if you have the limit as x goes to positive or negative infinity of the sum of the functions, the limit of the sum of the function will be equal to the limit the sum of the limits of that function. Okay. Nice property that says if your term here, your argument, can be broken into sums, each one of those sums can have their own limit. This one takes the limit of a product and says that this will equal the product of the limits. So the limit of the products will be equal to the product of the limits. Again, giving you the idea that you can break these up in many different ways, as long as you can turn it into sums or products. This next one says, if you can turn your argument into the quotient of functions, then this will be equal to the limit of the quotients. Sorry. The limit of the quotients is equal to the quotient of the limits. And notice as I go further and further, I get lazier and lazier. You don't see me putting the x approaches infinity or negative infinity here, but it's implied. And the last property is this. The limit of a root is equal to the root of the limit.